Alright, so the next phase of our GD&T series of video lectures. This one we're going to talk about reducing manufacturing costs. You know, it's kind of ironic when manufacturing people, sometimes if they don't quite understand GD&T, well, especially if they don't understand GD&T, when they see a drawing with a bunch of GD&T symbols on it, they get nervous. Like, oh, this is going to be expensive to machine. It's going to take a lot of effort. It's going to be really difficult to hold all these tolerances. But really the intent of GD&T is to, as much as possible, reduce manufacturing costs. Give manufacturing as much leeway as possible to move around, to be sloppy with their methods and quick and cheap, really, if possible. Whatever you can get away with, they want to let you. So we'll mostly look at the Hoffman article. That's like the Santa Claus article on this one, as well as the notes here. Well, maybe we'll go ahead and just get started. We'll try to reduce manufacturing costs. I'll give you two examples here, one related to form tolerances and one related to position tolerances. But first off, I'll just go over to the Hoffman article. Alright, so if you get that out, we're going to actually go, not part 1, we're going to skip down to part 2 and really look at this figure number 1 here. In fact, I'm going to blow it up on the screen. Oops. Alright, so this is the idea. It's a very simple part. I'm going to draw it up on the whiteboard. It's just, I think it's a square cross section, yeah, pretty much. 1/2 inch by 1/2 inch. And there's two ways we can think about dimensioning this part. Really, in the drawing there, it's type A or type C. B is just kind of an intermediate. It's the same as A with some notes on it. Actually, that's one of the things about, you can always tell a drawing that wants to be GD&T or wants to convey the function of a part but doesn't know how. They don't know GD&T because there's notes all over the drawing. Oh, I want this to be parallel to this, and this one doesn't have to be quite as online with that. And you can try to do GD&T with a bunch of notes. It clutters up the drawing. Really, the way to do it is with the symbols. Right? So A and C really are the traditional way, kind of the coordinate tolerancing, and then C is the GD&T tolerancing. So I'm going to put both of them here, kind of a one versus the other. And the top one, all it has is this dimension, 0.500 to 0.502, right? That's right. And we need to know what the intent of the designer was. And the intent, basically how this part's going to be used, the designer wanted the top and the bottom sides here to be really parallel to each other. Okay? So intent, or design intent, parallelism from top to bottom, 0.002. The top, the bottom here. So that if you put a plane on the top and a plane on the bottom, they should be exactly 1/2 inch apart, plus or minus 0.001, or within a 0.002 range, and that flat and parallel to each other. Now, in terms of this height, the 1/2 inch height, the designer's not that concerned about it. It's desired to be 0.5, a 1/2 inch, but if it's even maybe 0.49 or something, or 0.51, that'd be fine. So the second thing is that height really could be 0.49 to 0.51. Of course, the designer, though, doesn't want to put that as the tolerance there, because then we could end up with something that's basically not parallel, where it's 0.49 at one end and 0.51 at the other, and then it wouldn't be within this .002 parallel. So the designer here doesn't really know how to put both of these requirements in with just a coordinate dimension. So they figure, well, I'll just put in this, and that'll make sure that the top and bottom are parallel within 2000s. It's kind of an over-design. Back in the notes here, say that GD&T sometimes reduces manufacturing costs by over-dimensioning. I guess really what we want to say there, instead of dimensioning, is over-designing. Right? Designing it maybe with tolerances that are tighter than they need to be. Okay? Overly tight tolerances. We want to give the manufacturing people as much tolerance and leeway as possible, because then they're going to be able to produce that part with the least amount of cost. This designer doesn't know how to do it. They really want these things to be parallel, but all they have is size and location, so they specify this very tight tolerance to achieve it. What that means, though, in manufacturing is that we're definitely going to have to grind these surfaces. I mean, I can set these up on a milling machine and face mill them fairly flat, but in terms of meeting exactly this size, this height, it's going to be difficult. I'm going to have to set up the bottom and grind the height to get it exactly to that height. Because face milling, there's some deflection in the mill, and I can create a nice flat surface, no problem, but in terms of exactly setting that height, it's tough. I mean, you have to go down and start off and touch off the face mill and set the height and everything. So getting it within plus or minus 1,000th there, that's going to be pretty tough. I'm going to have to grind it. So this is going to mean grinding. Grinding is expensive. I don't want to have to grind. It takes too long. Now another way to do it is the GD&T approach, whereas here we can give a height tolerance of 0.50 to 0.52, or that's pretty much the equivalent of that, right? It's a plus or minus 0.01, 10 thousandths range, plus or minus 10 thousandths on the height. And then we'll define this bottom surface there as datum A, and say that the parallelism here, parallelism of this surface has got to be within 0.002 of A. So now we've got two separate specifications for our two separate requirements. Yeah, the parallelism's got to be there. This surface has got to be parallel to A, but that's not linked or tied up with the height of this block. The height's not that critical, 0.5 to 0.52. I can now just use a face mill to do this, because it's hard for me to set the height on the face mill, but I can get parallel surfaces, no problem. Okay? Face milling. It's going to be a lot quicker than grinding, and I can make a cheaper part. This designer didn't know how to separate parallelism with the height, and so they had tried to put it all in one dimension, and that leads to over-designing and making a more expensive part. The second example I have is on the same, right on the same page here. There's figure 2, and I'll draw that in the board too. It's just a hole in the corner of a block. Again, not very complicated. There's a block, the hole in it, and the regular coordinate tolerancing is given to the sides of the block. It's got to be 1 inch plus or minus 5, so 0.995 to 1.005. Okay? Same here. Right. And what we see in figure 1 is, again, kind of if I'm a drill operator and I'm going to come in and drill this hole, I can look at this these coordinate tolerances on the part and kind of imagine what kind of a zone I have or what's an acceptable error I can make in putting this in. Well, I've got some leeway left to right, and I'll just maybe represent this hole by its center axis because that's where the center of the drill is going in. I got some leeway left to right, and I got some leeway front to back. So I've got basically a square tolerance zone. Okay? Here's the target right in the middle, and there's a little bit in each direction there, left to right and front to back. We talked about this in one of the other videos that as a drill operator, it doesn't make all that much sense. I can be off in any direction. It's a little hard to tell. I can be off a little bit this way, a little bit that way, and a circle is maybe a little more obvious in terms of putting equal weight to being off in each direction. If I'm going to have a pin and a mating part that's got to fit in our circle, that mating part could be off in either direction, and my circle could be off, or my hole can be off in either direction. And so a square doesn't really represent it well, because a square is saying that, well, this hole can be off more in the diagonals than it can be straight up or straight to the side. That means like if I'm off on this diagonal, I have more leeway. It's not as important as if I'm off side to side or top to bottom. That doesn't make any sense. If I'm trying to fit things together, if they're off in any direction, that's equally bad. So it doesn't make as much sense. We'd like to somehow have a circle there. And so that's what the lower figure is. We, instead of using the coordinate tolerancing, we use a GD&T tolerance. If we draw this. So here's our circle. And for GD&T tolerancing, we're going to set some datums. So the lower surface is A, and this other surface here is B. And they actually didn't dimension this correctly. What they should have put in here is a box that says 1.0 and a box here that says 1.0. And those are called basic dimensions. Basic dimensions are theoretically exact. Which means theoretically, at least, we want this hole to be 1 inch from the bottom, 1 inch from the left. But I know it won't be perfect. So I add the feature control frame that you see in the drawing there, which says the position of that hole can be 0.014 from A and B. So that's what really governs how that hole is located. The position of it. That's a true position or a position function or tolerance right there. And it says that there's a zone. Again, we'll represent that circle just by its center axis. It says that there's a zone, a cylindrical zone. Because remember, that's the diameter symbol says it's a cylindrical zone. It's 0.014. 0.014. And that the center axis of the hole has got to fit in there with respect to A and B, meaning it's 1 inch over from B and 1 inch up from A. So that's what the A and B means with reference to those surfaces. But we come back to the basic dimensions here to see exactly where it's supposed to be centered. So those basic dimensions tell you that the center of the tolerance zone is there, and it's 0.014 in diameter. Now that makes more sense, a circular tolerance zone. If we looked at the other way to dimension this, it gave us basically a square tolerance zone with sides that were 5 and 5, or basically 10, right? And it would also be 14 on the diagonal. So on the diagonal, it's the same. But if we coordinate with GD&T, or dimension it with GD&T, we get all this extra area. That's more freedom for the drill operator to put the drill. it's looser tolerances because there's more play in where I drill. So just by representing with this circular zone, which makes more sense in terms of how the part fits together, it also gives me more tolerance. And it should result in a cheaper part. All right, so that is kind of the position tolerance part of it. We'll come back next time and we'll deal more with rule number 2.